presentations in one seminar. So, but now we have Jonathan Nguyen with a really fun talk about a unique opportunity to work with a system that has a bipartite representation, but is so small that it also has a trellis representation. And we can compare maximum likelihood decoding with LDPC decoding and look at how machine learning can help. So go ahead, Jonathan.
Yeah, hi everyone. Thank you. So I'm going to share my screen now. Okay. All right. Oh, that's wrong. Okay, so I'm trying to keep this a bit short. So hi everyone. Like I said, my name is Jonathan Nguyen, and today I'll be presenting my paper that was recently accepted to ICC 2022. The title of this paper is Neural Normalized Myths of Message Passing versus Viterbi Decoding for the CCSDS line product code. And before I begin, a huge shout out to my co-authors, all listed below here. All right, so before I get into the line product code or message passing, I first want to introduce the notion of bit disparity. So at its basic form, bit disparity is simply the number of transmitted ones versus the number of transmitted zeros. So for instance, if I transmit many more ones than zeros, my disparity will be very positive. Now in an ideal system, you'd want the disparity to be close to zero. Take, for instance, the converse of that. If we have a long run of zeros, that would constitute a low frequency component in our transmission. And because of that, we actually don't desire non-zero disparity because it introduces these low frequency components, which can constitute out-of-band transmissions. So you can see kind of like a proof of concept, making the running disparity, driving that to zero, would actually drive the low frequency component in the power spectrum density to zero as well. Now, finally, onto line product code. So why did I even bring up bit disparity? Well, that's because the line product code is actually a system used to manage disparity. And as an added bonus, it actually incorporates some parity bits for error correction. So here on this grid, we have 16 information bits denoted as E00 through E33. And some horizontal parity bits, PH, and vertical parity bits, PV. So PH are the horizontal parity bits, and they are said to have odd parity. Odd parity in this case simply refers to this constant XOR of 1 in the parity check equation. Additionally, PV are vertical parity bits with even parity, so that just refers to the lack of this constant 1 here. Now on to how the LPC actually manages bit disparity. So in order to actually manage bit disparity, recall that's the number of transmitted ones versus zeros, what the LPC transmitter does is actually keeps a running total of the disparity. So after each transmission, we can't always guarantee that the disparity will be zero in each transmission, but over the long run, we would like for the disparity to be zero. So knowing that information, we divide up the information bits into two subblocks, subblocks 1 and 2 here. And based on the running disparity at the moment of transmission, the LPC transmitter can actually decide to flip subblock 1, subblock 2, both, or neither. And it chooses which subblocks to flip or none based on which one would minimize the disparity of the running disparity. Now, note that if you flip a subblock, 1 or both, the parity check conditions are no longer satisfied. So now the question becomes, how do we determine whether or not the parity check conditions are, are violated because of channel noise, or whether because we flip the subblock? Now, one of the proposed solutions and the way that it's been done is actually to perform decoding 4 times. Each decoding kind of step or process assumes a different inversion of the subblocks. So subblock 1, subblock 2, both or neither. And the issue with this is that, obviously running 4 decoders in parallel isn't the most efficient use of our space. And then here's just a proof of concept that the LPC does decrease the running disparity. So you see that although the ensemble average of the LPC without kind of flipping the subblocks is 0, the variance is quite high. So at this given moment, our disparity even reaches about 1500. Okay, so one of the novel approaches of this paper is actually to reformulate the line product code as a linear block code. Now, first I should note that it's not quite linear in the sense that the constant XOR of 1 isn't typical with LDPC codes or linear block codes. However, what's unique about this is that we actually denote the state of the LPC encoder, which subblocks we flip via punctured bits. So the intuition is that why they're punctured is that when we receive the message, we actually don't have any information regarding which subblocks are flipped, because it's kind of, it should be, yeah, I guess the receiver has to figure that out itself. So that's why we modeled them as punctured. And because if we flip a subblock, we actually flip some bits too, and which is why that the punctured bits here connect to the subblocks for the horizontal and parity bits, or horizontal and vertical parity bits respectively. Okay. All right. And so now that we have a linear block code kind of representation of the line product code, one of the first things that we considered is perform maximum likelihood decoding on it. Now, the reason why we perform maximum likelihood decoding on this system is because you want to get a kind of baseline, or as like a metric of the best possible performance we can get. Now, note that we can't really do naive naive maximum likelihood decoding on the line product code, because as we know, we have 2 bits, or sorry, 2 possible values for each bit, and we have 26 possible bits. So that constitutes about 260,000 possible code words.
Well, I don't think you should say can't, because our corporate sponsor did that just to see how well, not that they were ever going to use it in their product, but they just wanted to, as proof of concept, that it might be worth considering not just treating this line product code as a way to improve the disparity, but actually to improve the decoding. We could take advantage of it. So they did do this crazy thing, and that was exciting. But then Lin Fong and Jonathan did better things. So go ahead, Jonathan.
Yeah, of course. Yeah, thank you, Professor, for that. Right, so I'm not saying it's not possible, but it's just not feasible to perform anywhere close in practice. And so in order to kind of decrease the number of required operations for maximum likelihood decoding, we actually turned to 2 papers. In both these papers, they actually transform the linear block code into a trellis representation. And using that trellis, they actually perform Viterbi decoding in order to get the maximum likelihood estimate. And as it follows, a simpler trellis would equate to a simpler decoding process. Oh.
Jonathan, is it possible to use Chase decoding algorithm for the product code here?
Yeah, that's actually a good question. I'm actually not too I'm actually not too familiar with Chase coding. Yeah. So maybe we speak after this to.
I'm saying that's a possibility also to be investigated.
Okay. Yeah. I'll definitely look into that after this presentation. Thank you, Darish. Okay. All right. So getting back to the presentation. Sorry about that. Right. So given our bipartite graph representation of the LPC, we're actually able to form a parity check matrix for that code. And so we actually leverage Wolf's paper in order to represent this linear block code, the LPC now, as a trellis. And I won't get into like the exact details of how it's done, but we can see, but I'll give a high-level overview of what it's trying to accomplish here. So essentially what Wolf's paper is trying to do is build up or build up the code word for one bit at a time. So here we start at the all zeros code word, and we calculate the syndrome, assuming that the first bit is 1 versus 0. And then from there, we branch off. So 1, 1, or 1, 0, or 0, 0, 0, and 0, 1. So kind of following the branch. And recall that for any valid code word, we have to satisfy that the syndrome is 0. And so that's why kind of we taper out at the end, because we only want to consider code words that have a 0 syndrome, because those are the only valid ones. Now, utilizing Wolf's work, we actually arrive at a trellis that only has 5,000 branches, which constitutes a very massive improvement over the 260,000 possible code words to check against in the naive approach. Now, we could actually do a bit better than this. So from Plus's paper, we can actually use the generator matrix in order to get a trellis for the maximum likely decoding. Now, at a very high level, from the generator matrix, we actually just perform permutations on the column of the matrix in order to kind of brute force the simplest possible trellis. And I say brute force because it's NP hard to actually get the best, the simplest trellis. But from a couple of our tries, we arrived at this trellis, which only has about 1,900 branches. So it's a over a half improvement over the Wolf trellis. Okay, so on the message passing. So now that we have the maximum likelihood kind of estimate as a reference, now we kind of want to move into the practical realm. You know, message passing algorithms are typically used in practical systems.
When we met with our sponsor, you know, we were so proud. We've got this Viterbi decoder. It's not nearly as complex as your crazy exhaustive search. And he was really excited too. He's a coding theory guy. And then he met with his FPGA team and said, we're so excited. We're going to do this Viterbi. We're going to use 19,008. And in the FPGA, he said, he was telling us about that meeting, and the FPGA people just stared at him and said, well, you know, that's cute, but we're still far too complex for this system. And so that's when we said, well, we have a bipartite graph. Let's use it. So go ahead. Sorry, Jonathan.
No problem at all. I appreciate the context. Yeah, so as Professor Russell said, you know, we tried to use maximum likelihood decoding with the trellis, and even though we got it so much simpler than kind of the brute force approach, it still wasn't good enough to put on an FPGA. And so that's the reason why we have to consider message passing. You know, message passing algorithms, I'll give a very brief overview here, kind of work by passing messages back and forth between variable and check nodes. And it's this iterative process that actually gets us a simpler decoding performance. So at a high level, variable nodes kind of represent the bits we get. They pass messages to the corresponding check nodes, updating them on what they think their beliefs are. Then these check nodes aggregate all these messages up. And given that these check nodes are connected via the paired check conditions, they can kind of see, you know, based on all these messages that it got, what each variable node, kind of how likely that the estimate was correct or not. Then these variable nodes update their beliefs based on the check node messages, and then they make a hard decision based on these new beliefs. And if that decision kind of satisfies the syndrome check, then we finish the coding. Otherwise, we just kind of restart. So this means for cleaner code words at a higher EB over N naught, the decoding process would take fewer iterations and be simpler. So it kind of scales better too for higher EB over N naught. Now for the LPC, we actually consider 3 message passing algorithms. And so the message passing algorithms kind of only differ in how the check to variable node messages are calculated. So at the first one we consider is belief propagation. At a high level, this is kind of the most theoretically accurate of the 3 we consider here, but it's also the most computationally expensive. this hyperbolic tangent operation and this inverse hyperbolic tangent operation isn't necessarily the most cheap to compute. And so we actually move on to normalized min-sum decoding. This is actually an approximation of leaf propagation, and it kind of sidesteps the hyperbolic tangents with this minimum operation here. And it's called normalized because we actually normalize with this constant factor beta here. Now, neural normalized min-sum decoding is actually something that's proposed in a paper by Lin Fong and I, and some other authors too. And the unique part of this is actually that instead of having this normalization factor be constant throughout every iteration and for every single edge, we actually allow it to vary according to which check node it originates from, or which variable node it's destined to, and also the iteration. And so computationally, min-sum or neural normalized min-sum and normalized min-sum actually have the same decoding performance, or not decoding performance, sorry, the complexity, because whereas, as I said before, maximum likelihood has the worst kind of performance. So out of all of these, obviously, min-sum without the normalization is the cheapest, but we don't consider it because it actually has pretty awful decoding performance. And these numbers here are calculated, assuming that every single message passing algorithm runs for the worst case 8 number of iterations. But, for higher E B over N naught, our number of iterations required actually approaches 1. So this isn't like it's just a worst case scenario. And we still see that message passing algorithms perform much better, even in their worst case, than the generator matrix trellis algorithm. All right, and so here are the decoding results now. So we can see on the top here, we have the frame error rate curves for the 2 iteration decoders. So normalized min-sum, belief propagation, and neural normalized min-sum. And since they're only given 2 iterations, they perform pretty awfully. Now, the more interesting case is the 8 iteration case. So you can see that kind of almost surprisingly, the neural normalized min-sum decoder actually gets quite close to the maximum likelihood decoding and vastly outperforms the belief propagation and the and the normalized min-sum decoder. And so for that reason, neural normalized min-sum was the decoding algorithm that we kind of move forward with. And so since we were actually doing this for a company and they wanted to put this in hardware, we wanted to make our decoding process kind of applicable and adaptable to be put in hardware. And so on FPGAs, fixed point arithmetic is used, meaning that instead of having like the 32 or 60-bit floating point or double precision representation in software, we were only given like 8 bits. And so kind of iterating through a bunch of kind of different combinations, we arrived at this quantization here, 6 bits for the integer part of our representation and 2 bits for the fractional part. And here are the results here. So we can see that we do get some decoding loss by performing this quantization, but it's actually fairly negligible, and the difference kind of minimizes as we get to higher E over N naught. So lastly, this isn't part of the paper actually, but it's something that I've been working on for my master's thesis, is in kind of intuitive reasoning as to why neural normalized min-sum actually improves decoding on the line product code so much. We actually get such a huge gap here. I think it's about a ½ dB gain. Why is that? And so like I said before, the neural normalized min-sum decoder actually assigns that weights to every check to variable node message dynamically. And taking a look at these edges and these weights, I actually saw that some of the check to variable node messages were actually zeroed out. And so looking at this further, based off of this, zeroing out a check to variable node message instead of this bipartite graph being, bidirectional, check to variable node and variable to check node, we actually kind of make it directed. And the effect of this, was that we actually broke many of the length 4 cycles, which for such a short block length code were the crux of not the crux, were like the pitfalls of decoding. And so the neural normalized min subdecoder recognized the detrimental effects of these cycles and assigned the weights in such to break those cycles. So just the extra knowledge. That's it.
Jonathan, this is very significant result, for the loops of length 4. I don't know if anybody else has done that or not.
I see. This is actually very interesting. So seems like you somehow avoid this 4 cycle, not by getting rid of the edges from the graph, but by scheduling the way that the message propagates, right?
Yeah, exactly. So we actually don't eliminate every single length 4 cycle. You can see that we still have this path from check node 1, kind of this length 4 cycle here.
Very interesting.
It would be really, I think it would be exciting for us, as part of our collaboration, if we had a particular LDPC code that you're interested in, we can explore, what is machine, because we've got all these tools kind of ready to go, and Lin Fong could even help, Jonathan could help lead that effort. We could go ahead and design the, do the machine learning, look at the result, and also try to figure out like what happened, and see, it may be that your codes are so well designed that we don't get this benefit because you didn't have those problems, but it could be that there are other problems that we are able to find. So, it's not clear exactly what's going to happen, but it's definitely worth doing.
Yeah, I see. Yeah, this is great results.
Yeah, and I guess adding on to Professor Russell, line product code actually wasn't kind of designed as an LDPC code. So maybe, for well-designed codes, we wouldn't have this.
Yeah, I've seen a lot of maybe short codes because LDPC is known to be not good for short codes. And for short codes, people do a lot of algebraic coding. And, because almost all the known algebraic codes, in terms of the bipartite graph, they have 4 cycles, right? And then the BP or the message passing is not working, right? And I've seen people doing some tricks by adding a lot of redundant rows, and by doing that with the message pathing, and it's approaching ML. But I think you have a totally different way by scheduling the message propagation to avoid the 4 cycles, and it's working. That's very amazing.
Yeah, we're really excited about it. And it was kind of fun because we wandered into it by working on basically a toy problem that just happened to be presented to us, but
this might be maybe connected to one of the very difficult problems in the coding field, which is to introduce redundant rows. So I think if you want to avoid 4 cycles, by adding redundant rows, right? And you're going to get coding gain, and that's for sure. So we have done some works before, but things becomes much more difficult, in order to avoid those 4 cycles, right? So if we have a way to, decode with 4 cycles, maybe by your methodology, right? And that may help us, get a lot of redundant rows to get the coding gain.
Or not even have the redundant rows.
I think it might be impossible for the, let's say 4K byte length and the column weight. Potentially higher the column weight, easier to do it. And also the shorter the length, easier to do it. I think Sarah Johnson, she has some very good results in terms of how to add those redundant rows, and I think it's related to the EG and PG kind of interpretation. but it turned out to be quite difficult for the long code and low column weights. Anyway,
You
so
are
I
correct.
think
It's very important having this redundant rows for certain cases.
exactly we see amazing gains by
Yeah.
adding those redundant rows.
Yeah, Jonathan, I gave this comment before to you, but when you are doing simulation, you're considering different code words, right? Transmitted code words.
Yes.
Okay, so you are okay because make sure that when you're changing the decoder, there is no bias with respect. If some people considering all zero and providing some modification which may not be true for all code words. And another thing that you mentioned about the syndrome, you checking syndrome every time, or you doing at some maximum iteration?
Yeah, we're doing syndrome every time.
Every time. The only thing is to make sure that the undetected error probability is low enough, because otherwise you get undetected code words.
Right, I see. Okay.
Okay, and it looks like we have a question from Sahil.
Yeah, actually, I was just gonna get to that. Yeah, so sorry. So what I mean by zeroing out the edges is that, so these check to variable mode messages are weighted by this constant beta factor here, or that constant, but this a beta factor that's kind of unique to each edge. And so by zeroing out, I just mean that this beta kind of is a very, very small number, close to zero, so that this message kind of goes to zero and doesn't really contribute to the aggregation.
So you can, like, if you zero out an edge to a variable node, it just means that that variable node is going to not include that information when it makes its decision.
Exactly.
And that's just like it's like that. It just doesn't pay attention to that check node. Of course, if you zeroed out an edge into a check node, it would kill the check node. But if you zero out an edge into a variable node, it just means that the variable node will look elsewhere for its decision.
Yeah, that makes sense. Yeah, I noticed that when we were doing the quantization, there were quite a few edge weights that went to nearly zero when you quantized it 6.2.
Exactly.
Yeah.
Anyway, again, I'm saying that, this result is very significant, Jonathan. Congratulations.
Yeah, it looks like we're going to have a fun, I think it's, so this is kind of the horse that Jonathan can ride for the rest of his master's thesis, to figure out, what's causing, how the machine learning is helping. And yeah, so that's really exciting.
I have a question for Jonathan. So can you briefly describe your training process? I'd like to have an intuition about the complexity of the training.
Right. You mean to train the weights of the neural network?
Yeah.
Okay. Yeah. Linfeng, also feel free to jump in on this if you have any comments, or if I'm saying something that's not quite accurate. So in order to kind of right. So first, we kind of like build up the kind of, let me think about this. So in order to represent the message passing process in kind of a node form, we first have kind of flatten it out. And so we do is kind of represent each variable node as an input and kind of branch it off into different operators, like kind of summation operations, multiplication, minimum operations. And that kind of gets us a flattened out structure of the message passing algorithm. Given that, we can actually perform back propagation, kind of, because we can go one way to get to our final result.
Okay, so you mean you unroll the message passing process?
Exactly, yeah.
So for example, for your 2 iteration result, you have a 2 segments, 2 bipartite graph connected together somehow, right?
Mm-hmm.
If for 8 iteration, you have 8 of them connected together.
Actually,
so
you can
computational graph.
Yeah, actually, you can do it iteratively. You can do the backward propagation iterative. You can just use one bipartite graph to do all. I mean, you don't have to So
Okay.
basically, in the yeah.
But
So
that means
because the graph
in every
looks the same. Okay.
yeah, they look the same. Yeah.
Exactly.
But each graph is like a layer. So you do
Right.
the bifurcation iteratively.
Right.
Right.
And by the way, we built the training system using C++ by ourselves. We didn't use the TensorFlow or PyTorch to do the training.
So what
It
is
is.
your input feature and the output loss function?
The input is just you assume that there is all zero code words and you add noise. And so these are the labels, right? The labels of this variable nodes, they're just all zeros. And the loss are cross entropy.
Entropy.
Yeah.
The label is all zero code words, and the feature is noisy code word essentially.
Right.
Right. And what's actually interesting about the training process is actually we have to specify, because our inputs are noisy code words, we have to specify the SNR or the EB over N naught at which the network is trained. And from kind of empirical results, selecting the right EB over N naught to train over is actually kind of affects performance greatly. And so for this one, we actually chose about 4 to 4.5 dB for our training range. But for kind of a longer block length, maybe you would want to train it at a lower or higher one, depending on how steep the waterfall is.
So Jonathan, if you have 8 iterations, right, and the weights or the edges in the network, I mean, for every iteration, the weights might be different, right? So it's represented by different edges in the neural networks, right?
Mm-hmm.
I see. I think for this kind of scheme, storing those weights efficiently in the hardware.
Yeah.
So actually, we found that, I mean, one problem is for the long block length LDPC code, right? It is not possible to store the weights for all of the edges in 10 iterations. So we found that these weights are actually related to the node degrades. So you can use weight sharing. So such that
weight sharing, it's a must. Yeah.
And actually, even though you use weight sharing, it gives you the lossless performance. Compared with using the edge specific weights.
Okay, that's great. Yeah.
Yeah. In this case, we'd use edge specific weights just because it's a very short block length code. And so I think there's only like 52 edges, but yeah, like as Long said, for longer block length, it's pretty infeasible. And kind of as a side note too, I guess for my thesis, I wanted to kind of isolate the effect of zeroing out these edges versus kind of the effect of the dynamic weights, because normalized min-sum kind of fixes that normalization factor to some constant throughout every single iteration. So I wanted to see, could I still get similar performance if I zeroed out these edges here, but instead of having these edges be dynamically rated, just fixing them to some constant. And actually I found that, at least for the LPC, the performance was very similar, maybe about a 0.1 dB loss only.
Jonathan, just a quick follow-up. Can you go one slide afterwards? The one on, I know we talked about the zeroing out of the edges. So you said in your discussion that zeroing out makes the edges, like the ones that you've labeled with an arrow, makes them go in one direction instead of them being bidirectional, like you'd see, let's say, between number 4 and number 2. So I was wondering, if you zero it out, wouldn't its effect, like technically, quote unquote, completely disappear? How would it just be one direction instead of bidirectional?
Right. And so taking a look at a particular variable node 10, so variable node 10 can still pass on its belief to check nodes 5, 6, and 7. And those in turn can affect variable node 1. However, variable node 1 now, which was punctured, can no longer affect variable node 10 through the same process, because we're not allowing the message to propagate from variable node 1 through 5 back to 10.
Oh, okay. So 10 can pass its message to 5, but then 5 can't go back to 10. That's why 1 can't communicate with 10, is what you're saying.
Right, exactly. And
Okay,
this is kind of a subgraph. So this doesn't represent every single variable and check node,
Mhm.
but this kind of gives, but these are all the zeroed out edges though.
Okay, that makes sense. Okay, thank you.
Definitely variable nodes should be connected to these checks, otherwise will not satisfy
Exactly.
the code constraint.
Wow. So that's really, I think it's really exciting. And I think I was just mentioning, Fan, I just wanted to introduce you. I don't know where she is on your screen, but Samira Galayasovic is with us here today, and she's a new doctoral student. That might be, this might be an area where we could, if it works out, that she could begin working with Lin Fong and Jonathan during the spring quarter and maybe come to SK Hynix over the summer.
Okay, I see. Yeah, nice to meet you. So yeah, we're gonna work together for sure in the future. Yeah.
So anyway, I think it's time. People have been very patient to stay over. It's my fault for having set up 2 talks. Even though they're supposed to be 15-minute talks at ICC, I should have known that we would have great conversations. So this means we might need to revise our plan for next week, where we were going to have 2 talks. But anyway, that's it for today. I want to thank our 2 speakers, Lin Fong and Jonathan. So much fun. And I love the participation that we have by our experts in the community that chose to join today. So thank you so much. And with that, I'm going to go ahead and stop the recording.